Okay, I am ready to finish 9-2 day 2 directions for telescoping series. We got through problem A and B, so let's pick up on C and discuss whether this looks like it could be a telescoping series. Maybe initially you might say, well, it doesn't look like it would be. However, if we use the notion of partial fractions, we can double check to make sure that it is not a telescoping series, or perhaps it is. So I know that the polynomial shown in problem C will factor into an n plus 1 and an n plus 3. I could even go one step further and say that I'm going to do that partial fraction decomposition where I break it into two completely separate fractions. Now, the method for that, in the past, we said that 1 is equal to a n plus 3, added with b n plus 1, where we multiplied both sides by this and came out with this. So now, if I let n equal -3, I would get a 0 for my first term and put in -3 for my second, and this will be -2b equals the 1 from the left side. Therefore, b is -1/2. And if I go back and, and work n plus 3 plus b, n plus 1, let b equal, or let n equal -1, then I will have this going to 0, and I'll have 2a equals 1, and therefore a is equal to +1/2. So we get our two values for partial fraction decomposition. So let's just fill in our a and b. A we said was going to be 1/2, b was going to be a -1/2. Now, since they have 1/2 in common, I think I'm going to elect to pull that 1/2 all the way out front and have n equals 1 to infinity. That'll give me a 1 over n plus 1 minus 1 over n plus 3. Picking up that negative in the middle there. Now let's go into expansion and let n equal 1 to start things off. When I put 1 in, I'm going to get 1/2 minus 1/4. The next terms, when n equals 2, it'll be a plus because we're summing up the series. So let n equal 2, and we're at 3 and 5, so 1/3 and 1/5. Oops. How about a minus in there? Let n equal 3, and I'm at 1/4 minus 1/6. And let's do one more. Plus n equals, we're up to n equaling 4. That'll be a 1/5 minus a 1/7. And I can pick up the pattern from here. Looks like it's evens and odds and evens and odds. Okay, 1/2. Does it have a minus 1/2 anywhere? No. But I have a -1/4 and a +1/4 adding to 0. 1/3 does not have a -1/3, so that's going to stay. -1/5, +1/5. -1/6, +1/6 would be the next. -1/7, and I'd have a +1/7, and so on down the line until I got to the point where I was n plus 1 minus 1 over n plus 3. And you're probably wondering, well, what about those very last terms? Well, recall that we're going to infinity. So if I'm out here at infinity, these are going to be so tiny that they are not going to impact the overall sum. So we would have 1/2 plus the 1/3. And that is big ink. And that's going to equal 3/6 plus 2/6, giving me 5/6. However, we don't want to forget about our 1/2 way out front, and I probably should have just put that in along the whole way so that it would be impossible to forget. So our overall answer is going to be 5/12. So not only does this series converge, but we can actually come up with the sum that it converges to, which is 5/12. So problem C converges by the telescoping series test. All right, the next topic, topic 5, is the harmonic series. The harmonic series refers to one particular type of series, and we have examined this particular sequence before, the 1 over n sequence. If we expand it out, we know we come into 1, 1/2, 1/3, 1/4, and so on. If we sum those up, we will find that our series diverges. The harmonic series is divergent. It doesn't go to zero fast enough to allow us to capture a finite sum. So this is a divergent series. It is one you'll want to memorize as divergent. Because if you relied on the nth term test, which I told you is a great test because it's fast, such as the limit as n goes to infinity of 1 over n, well, 1 over n as we get super large does indeed go to 0. But remember, that's not a conclusive test. We cannot determine whether it converges or diverges. And in this case, it's divergent. So, if you're handed a series where it's like 5 over n, 10 over n, 1/2 over n, you can very quickly say that this is a divergent series. Even though it isn't specifically a harmonic in a sense that it's just strictly 1 over n, we can turn it into harmonic very quickly by pulling this 5 out front. And that is a legal move. There's a property for series or for summations where if we have a multiplier, we can move that multiplier in front of our summing and multiply after we sum up all the terms. And you might ask yourself, how is that possible? Well, let's just take 5 over n, for example, and lay that out. It would be 5 over 1 plus 5 over 2 plus 5 over 3 plus 5 over 4. I think you get the picture, plus some value 5 over n, and so on. Notice how they have a 5 in common? We can GCF that 5 so that I can sum it by looking at each individual term or the harmonic series and then multiply by 5. So indeed this 5 can be brought out front and get the same answer as if we had left it in there the whole time. Okay, kind of a long explanation, but I wanted to demonstrate that property. So this one would be this series, let's call it S. The sum of this series is divergent because it is a harmonic series. And all harmonic series are divergent. Letter B is just a little bit different. It looks harmonic. However, this one starts at 4, whereas up here we said the harmonic series is starting at 1. So is it still divergent even if it starts at 4? Well, yes, I think your common sense would probably tell you that it wouldn't matter where it started. This still would be divergent. And you could prove that real quickly if I started it back. Let's say I started it officially back at 1 and had 1 over n. We know that that is divergent. So this is the series 1 plus 1 over 2 plus 1 over 3 plus 4, 5, 6, 7, which then I could bring in my series that we wanted to talk about starting at 4. And this, if I sum these first 3 terms up, I would get 11/6. So I'd have 11/6 plus whatever that might sum to. We know this is divergent. This is divergent over here on the left. So can divergent equal 11/6 plus some other and become convergent? I don't think so. So if I subtracted like 11/6 from each side, I still would have divergent. Some unknown sum minus a specific amount is still going to be some unknown sum. So we can prove then that the sum from n equal 4 up to infinity is also divergent. Finally, our last example is kind of an application example about a bouncing ball and trying to capture what the total distance covered by our bouncing ball is. Do you think it's possible to sum that up? Or is it just too much that it would never ever finish and we wouldn't be able to get a sum on it? Well, let's read the problem first. A super ball is dropped from a height of 24 inches and allowed to bounce until it comes to a rest. On each bounce, the ball rebounds to 75% of its previous height. Find the total up-down distance traveled by the ball. Well, let's just think about this. If I drop the ball, the first distance it covers is 24 inches. On bounce number 1, it's going to cover 18 plus 18. On bounce number 2, it's going to cover 3/4 of that 18, and then 3/4 of the 18 when it comes back down. On bounce number 3, it's going to have the previous bounce times 0.75 for this third bouncing, plus 18. Oh, you know what? I'm sorry. I should have done 24, shouldn't I? Let's go back to 24. 24, it would work either way, but I think this might make more sense to you. 24 times 0.75, which is the 18 that I happened to grab from when I looked over there. The next bounce is going to be the 24 times 0.75, and then that was the rebound from bounce 1. Bounce number 2 will have its own 0.75, and we'll repeat that same pattern, right? Bounce number 3 will be take bounce 2, 24 times 0.75 times 0.75. There's bounce 2 height, and take 3/4 of that, 0.75. And I think you can see the pattern here. It looks like we've got 24 as our starter value, and then 0.75 n on that. I could sum that up from bounce number 1, which would get me the 18, wouldn't it? Because the first time this happens, it's going to give me the 18. So I would want this to start at 1 and go to infinity. But I've got to capture not only the up position, but also the down position, which is the same height. So let's double that. And then what I haven't captured is the actual 24 from the dropping. And I didn't want that to be part of the doubling, so I'm going to put it out front. And this would give me my total distance traveled. It is a geometric series, isn't it? So we'd actually be able to come up with the total sum for this. Well, that's incredible. Okay, so we got 24 plus. Let's bring that other 24 out, double it, and we're up to 48 because I multiplied the 2 and the 48. Equals 1 to infinity of, well, let's go 3/4 n. And then we can see that r, the absolute value of r, is equal to the absolute value of 3/4, which is less than 1, and therefore this series converges by the geometric series test. We can actually get a sum on this. So the sum of our series is equal to 24 plus 48 times. Now, let's do the calculation of this particular sum. My first term starts with a sub 1, so I put a 1 in here, and my numerator will be 3/4, and it's 1 minus the ratio. So we're there, aren't we? Calculate that. 24 plus 48 times 3/4 divided by 1/4 is like multiplying by 1/4. And 24 plus 48 times 3, 24 to 144. Looks like we are at 168 for total inches traveled. Total distance will turn out to be 168 inches. Cool. Well, homework, you guys, is the worksheet that follows. These are the problems taken from the textbook, and just an intermix of nth term test. You might have some harmonics in here. You might have some telescoping series, which I would probably try to expand and look at the terms. And sometimes you might have to do partial fractions. And also there could be some geometric series sitting in here. Those are the tests that we've focused on so far. So that's what you should expect. I think it's a very good habit to get into is to look at the nth term test first and do that test where we take the limit as n goes to infinity of whatever our series is and see if it equals 0 or does not equal 0. If it does not equal 0, game over, it's divergent. Now, sometimes I can tell very quickly off geometric series as well, because geometric series, if r is not less than 1, it's divergent and game over. So look for patterns. Also, because we're in the Larson textbook, you can go to calcchat.com. We are in the 8th edition. And you can select 8th edition and you would be able to see solutions to any of these odd problems. Whoops, sorry, 66 is not odd. And see the steps that they took to solve the problem. So that might be a helpful thing when we're in this series section and we're working on a last year's textbook. All right, have a great day.